Okay, last video we talked about overfitting or overtraining. And we'll review that in a second, but the goal of this video is to see some tricks for how to manage or combat that overfitting. So we saw that if a model has enough degrees of freedom, it can become hyper adapted to the data set, the training set, and start to fit the noise in the training set. And in that case, what you see is that the training error is very small. What do I write that? Training error is very small. The problem is that the model doesn't generalize well because it was so focused on the noise, and the test error on data that it hasn't yet seen is actually quite large, quite a bit larger. So the test error is much larger than the training error. So there are some strategies to try to stop our network from trying to fit that noise in the training set. The first one I want to talk about is regularization. So you might have heard of regularization in context of other courses and other optimization problems. So we're going to talk about one that leads to what we call weight decay. So we can limit the overfitting or the capability of our model to overfit by creating a preference for solutions that have smaller weights. So we're basically saying not any solutions equally preferred. We prefer solutions with lower, smaller weights. So we achieve this by adding a term to the loss function that penalizes for the magnitude of the weights. So let's say our loss function before was E. Now we're going to create a different one, E tilde, and it's going to take the Y as input as well as the target and the model parameters. Now it's going to be the old loss, or the old cost function, but we're going to add to it lambda bar over 2 times what we call the square of the Frobenius norm. So this Frobenius norm is like a 2 norm, except it's a sort of matrix version of it. Okay, so normally when you have a matrix of numbers and you take the norm of that matrix, there are some different induced norm things. It's all about matrix multiplication and what that matrix does when you multiply it by a vector. In this case, though, Frobenius norm is basically just sum of the squares of all the elements. So, for example, I'll define it. Frobenius norm of theta is the square root of the sum of all the elements squared. This is the Frobenius norm. Frobenius norm. Okay, sum of over all the weights. Okay, so it's the new cost is the old cost plus this term that penalizes the Frobenius norm of the weights. So it's going to prefer smaller weights. So how does this change our gradients? So if we were to take the gradient of this E tilde with respect to theta, we can break it into the gradient of our other E plus, now looking at the gradient of this term over here with respect to theta, and the 2 comes down and it basically turns into lambda bar times theta. And in fact, this can all be applied on an individual element basis. So now in terms of an update rule, this basically says that theta I gets updated with the old value of theta I minus some step size times the gradient of E with respect to theta I minus lambda bar times update times theta I. Sorry, lambda bar times the step size times the theta I. And so I observe that this thing over here is actually just one constant. So often what we do is we separate them. We collapse them into a single constant. Which is why I had the lambda bar before. Instead, we'll just talk about lambda by itself. So with this update rule, we're basically each weight is updated according to the gradient of the cost function, but then we just subtract off this part here, which is kind of like a decay. If you know anything, if you've tinkered with differential equations before, this is a decay term. So every time you update it, you sort of pull it down a bit closer to zero. If you're positive, you pull it down towards zero. If you're negative, you pull it up towards zero. It's always decaying towards zero. Now, when we apply this updated weight decay regularized update function, update rule, you can see that our fit of our small blood sugar data set is far less precisely hitting those points now. So you can see here the original overfit version. And what I'm also showing is this one here, which is the regularized with weight decay. And it's kind of interesting to look at the weights themselves. Well, first of all, let's look at the cost. The original loss, now this was on the, if you look at the training set, the training loss is really small for the non-regularized overfit version. We don't really care about the training loss. What we care about is test loss. So when I run each of those two different models, the blue one, overfit, and the regularized one, through with some test data, I get a lower test error or test loss on the weight decay version, on the regularized version. So you can see this, the weight decay version is 0.012, whereas the original one was 0.017. So that's good. And you can see just from the plots that that the orange line is not trying to fit those specific points very closely. Now looking at the weights themselves, the unregularized version, if I were to add up all the, or if I look at the Frobenius norm, it was 254.4, the squares, some of the squares of the connection weights and biases. Now, if I use the regularized version, it's quite a bit smaller. It's 7.1. So maybe I should just label these. Okay, so it did indeed lower the connection weights and biases quite a bit. We're limiting the solutions that we can achieve by preferring connection weights and biases that are smaller. And so it's got to do this balancing act to try to achieve that part of the objective, this part over here. It's got to try to balance achieving that with achieving that, trying to minimize both of those. So in this model, lambda controls the weight of the regularization term. Now there are other types of regularization terms. You can also use the L1 norm. So for example, the L1 of theta is the sum over the elements of just the absolute value of the elements. The L1 norm tends to favor sparsity. Most weights are close to zero with only a small number of non-zero weights. The L2 norm, that I just showed you, the regularization with the Frobenius norm, you can get quite a few small weights, very few large weights. The L1 norm is more like things are either zero or they're more decidedly not zero. Just has a different flavor. Data augmentation. Here's another thing that we can do to try to avoid overfitting or overtraining. Another approach is to include a wider variety of samples in your training set so that the model is less likely to focus its efforts on the noise of a few. Now, this would seem like an obvious thing to do. So in the case of my blood sugar and dose data set, 6 points obviously is not a very comprehensive view of the underlying phenomenon. So obviously you would want to have more points. And indeed, if you train the model on more points, like these 300 training points, then we get a much more robust model, this orange one here. The augmented loss goes down to 0.00934, whereas the loss on our original model that was fit to those 6 points, its loss on its test loss is, as I said before, 0.017. So you can see the line is much closer to the middle of the cloud of points that reflects a more statistically comprehensive view of the underlying phenomenon. Now, where does this data come from? Now, I created this sort of silly scenario where we have a very small data set and it fits the noise, obviously, when you're overfitting. But you might think, what about other situations? So for things like image recognition tasks, and we will play with some of these later on, you can generate more samples from your training set by just applying little shifts or little rotations to your input images. So one can generate more samples by shifting or rotating the images. Those transformations presumably do not change the labeling, but they do change the input images. So you could take a data set of, let's say, 200 images and generate 2,000 images just by having different shifts. And you can actually play with contrast and brightness and whatever it is you want to make your model invariant to, you can change your input along those dimensions. And that'll allow you to augment your training set with more data. Okay, finally, we'll talk about dropout. Dropout is kind of a strange solution to the overtraining phenomenon. It's kind of bizarre. So while training using the dropout method, you systematically ignore a large fraction, typically over half of the hidden nodes for each sample. Normally, this is the case on the last hidden layer. You cut out or ignore or remove or zero out more than half of the nodes, and you try to still generate your output. Okay, so for example, given a dropout probability of alpha, then each hidden node will be dropped with a probability of alpha. So that might be 80%, 0.8. So a drop node is temporarily taken offline and set to 0 for that particular sample. And then we do a feed forward pass and then a feedback pass or a backprop pass with those neurons just missing in action. So for example, on the left here, I have the original net. So there's no backprop here. Okay, so we've got this last hidden layer H's and these outputs Y, and they'll be, we calculate the output nodes by sigma of Z, the input current Z. And let's just say the hidden layer's got N nodes in it and the output layer has K nodes in it, just to create some variables so that I can write some formulas later on. Okay, that's the original network setup without dropout. Now let's consider a dropout network on the right here. And in this last layer over here, I'm going to say alpha is the dropout rate. Alpha fraction of hidden nodes removed. From this layer here. Now I'm going to refer to the remaining hidden nodes as script H, like that. And I'm going to define script H sub n is equal to 0 with probability alpha This is on an individual node by node basis. Or it's equal to hn with probability 1 minus alpha. So if alpha is 0.8, 80% dropout rate, then there's an 80% chance that each node will be a 0, and then a 20% chance that the node will be what it was supposed to be ordinarily in the normal network. And let's just define some output here. Y is sigma of Z bar. So Z bar is going to be the new input current after we've dropped some of these nodes. Okay, we do both, with these dropped nodes, we do both a feed forward and a backprop pass with this diminished network. So I'll talk a little bit later about why this is a good idea. But right now, let's just finish talking about how we implement it, and then because there's an important thing to consider here. Consider the absolute input to the nodes in the output layer. So without dropout, in this scenario over here, if we think of kind of statistically speaking, what would the input current to the output nodes be? Let's call it this big bubble Z. Is going to be the sum over the output nodes of the absolute values of the input currents. Let's just say for some reason we want to calculate that. And we could calculate that like this. H times the connection weights. So let's call these connection weights W here. W, and we're going to take the kth element, absolute value. So we're just adding them all up, adding up the input currents to the output nodes. We're going to call that the bubble Z. So with dropout, that's without dropout. With dropout, we've removed a bunch of the input currents, right? A lot of the nodes are going to be 0, so there's going to be no current coming from them. So with dropout, adding up that thing, k equals 1 to capital K of these Z bars is going to be scripted H times W. And now the scripted H's with probability alpha are going to be 0. And so since we're looking at the expected, I've got this, I sort of saved myself by saying expected absolute input. So this is the expectation over doing many experiments where we're dropping out different nodes at different times, okay? Over the long run, we would expect each node to be 0 alpha of the time. That means it's non-zero 1 minus alpha of the time. So the input current to the output layer would include the 1 minus alpha, the nodes that were not zeroed out. So this is all 1 minus alpha times bubble Z. So if we're removing, if on average, if each node has an 80% chance of being dropped, that means only 20% of the current is making its way through to the output layer. And that's what we're seeing here, 1 minus alpha. So a dropout rate of alpha reduces the expected input to the next layer by a factor of 1 minus alpha, which could affect the behavior of the next layer. So let me explain that. Let's say we've got input current to the output layer of Z without dropout, and we've got this activation function that looks like this. Like the some output node has an activation function like that. So given that Z, here's the output that we would expect when there's no dropout. Now if we do a dropout, let's just say a 50%, then we're talking about a Z bar down here. Now look what the activity of the output node will be. It's quite a bit different. It went from this level down to this level only because we dropped out a bunch of nodes. Now that's going to change the behavior of the output node. the change in the input causes the change in the activity of the next layer. The thing is, after training, we're using Dropout to avoid overtraining. Ultimately, we'd like to use the full network without Dropout and use that as our model and hit that with the test data or new samples that we hadn't seen before, and we want that to work properly. So we're only interested in the Dropout for the sake of training. Quick joke break. I was at a job interview recently, and the interviewer looked at my resume and said, "Wow, what's this 4-year gap in your resume?" And I said, "Oh, that's when I was at Yale." And the interviewer said, "Wow, that's really impressive. You're hired." And I said, "Oh, thank you so much. I really need this job." So after training, we want the network to work without the drop nodes. So we have to train it as if the currents that it's going to be receiving are the full currents, not the dropped out currents. So the weights learned with Dropout will not work properly in the full network. Solution is to scale them up to sort of compensate for the dropped nodes. Okay, so we scale the output of the Dropout layer up by a factor of 1 over 1 minus alpha. Right? If the input current is 1 minus alpha of what it should be, well, we divide by 1 minus alpha to scale it back up again. So for example, if alpha equals 0.8, the number I've been using, then 1 over 1 minus alpha is 5. Okay? Right, so the Z bar would be 1 over 1 minus alpha times the scripted H, or the dropped out H, times the connection weights. And so this, if we were to add up now the total input to the output layer, we would get back to our bubble Z again, which is what we want our network to function properly as against a regular, a future data set, a test data set. Okay, we can accomplish this by adding another layer to our network. So I pitched it as if we're going to take this layer here, and we're going to drop a bunch of the nodes. Whoops, where'd it go? Okay. But in terms of implementing it, it's actually more convenient to actually just add a layer after that layer. So that layer that was outlined in blue before now was kind of split up into 2 separate layers. And we calculate H, the original H. Now this new layer is going to hold our scripted H's. And this will be our dropout layer. Okay, in terms of implementing it and creating the network in the actual code, this network will actually have 1 extra layer fit in there. The activation function for that layer. So we treat it just like any other layer, and it has its own activation function. Of course, the activation function is chosen to implement the dropout. So the activation function is D of H, right? It's going to receive, obviously there's no wild connection weight matrix here. It's just a 1-to-1. So these are the normal pointwise activation functions, pointwise layer, I guess. In terms of PyTorch, it's not a linear layer, it's just a layer. So the activation function is 1 over 1 minus alpha, scaling up the current, times H alpha. So I'm using this notation to represent the H's are dropped with probability alpha. So it equals 0 with probability alpha, and H with probability 1 minus alpha. Okay, so during backprop, so we can create a layer using an activation function, and as long as that activation function knows its own derivative, we can build it into our PyTorch auto differentiation stuff and just apply those, apply the activation map and know that when we do our back prop, when we call backward, it's going to push the gradients through that layer accordingly. So we know that the scripted H from the dropout layer will be applying the activation function to that. And ultimately, when we call the, when we look for the gradient of our loss with respect to that layer H, we'll have to go through that dropout layer. So the scripted H times the derivative of the scripted H with respect to the unscripted H. Okay, now that derivative, what's the derivative of that function? Well, for any node that was not dropped, it's basically just 1 over 1 minus alpha. That's the derivative. If H was not dropped. So what if the node was dropped? What would we expect the gradient to be through there? I guess the question is, for any node that was dropped, how does the output error depend on that value that was dropped? It doesn't at all. It had no influence on it. So the gradient is 0. Okay, so in my experiments, I've implemented this. So of course, PyTorch has an implementation, has various implementations of this. In my implementation, which is kind of the simplest version, I ran the 6 sample blood sugar data set through and used a dropout rate of, I think, 85% or 90%. I had to adjust the learning rate in order to keep it stable. Because if I'm using a dropout rate of 90%, that means it has a multiplier of 10. This 1 over 1 minus alpha becomes 10, right? So you have to make sure your learning rates aren't going to combine with that factor of 10 and destabilize things. But the dropout test loss is 0.011, and the original non-robust model, this blue one, which was trained on that test data set. Well, they were both trained on that. Sorry. In terms of test loss, I trained both models on these 6 data points, but as we saw before, the network that was not regularized at all, or that didn't have any constraints, its test loss was fairly large, 0.015 in this case. The one that had dropout, this orange one, you can see it's a bit smoother, doesn't stick to those training points quite so much. Its test loss was 0.011, smaller. Okay, so why does this work? Why does dropout work? There's a couple different ideas. One is that it's akin to training a bunch of different networks and combining their answers. Every time you run it, you get a different set of dropout nodes. And so you're trying to train all these various networks together, and essentially their answer, for them to perform well, it's kind of an average performance over all of those various dropout networks. So each diminished network is likely a contributor to this consensus strategy. Another way of looking at it or thinking about it is the dropout disallows sensitivity to particular combinations of nodes. So instead, the network has to seek a solution that's robust to loss of nodes. If you click on this link here, it will take you to a paper that I'm showing here. It's improving neural networks by preventing co-adaptation of feature detectors. So feature detector is kind of like a hidden node, I guess you could say, and it's kind of recombining all the information from the input into some feature that can be useful for classifying. So I like this idea of co-adaptation. So the dropout prevents complex co-adaptations in which a feature detector is only helpful in the context of several other specific feature detectors. So I guess you want to, in terms of generalizing, you don't want your feature detectors or your hidden nodes to be too specific to stuff in your input data set. And in a way, it's the same idea as overtraining or becoming sensitized to the noise in your input data. Anyway, however you want to interpret it, dropout seems to help. And it's a common technique that's used to combat overfitting.